Hello. Hello, everyone. Welcome to the second session of the Haskell Symposium. Our first speaker is Patrick Redmond from the University of California, Santa Cruz, and he's going to present the paper, An Exceptional Actor System. Please, Patrick, take it away.
Hi, can you hear me? Thank you for coming. I'm going to speak fast, so wave at me if I'm speaking too fast. Okay, I will endeavor not to. As Facundo said, I'm a third-year PhD student at the University of California, studying with Lindsey Kuper. And today I'm going to tell you about how to implement an actor system in like 10 to 20 lines of Haskell code. So we're going to implement actors. Actors are nodes and message passing, more or less. Except today we're going to do the message passing with exceptions. And we're going to do this with ingredients taken from the GHC runtime system. We're not really adding anything. It's all already there. So the plan is, I'm going to do a brief review of exceptions in Haskell. Then I'll talk about distributed systems and actors a little bit. I'll show you the implementation, and then hopefully have time for a demo. Everybody loves exceptions. Try to divide by 0 and resume, and you're fine. Who here is familiar with exceptions in Haskell? And who here is familiar with asynchronous exceptions in Haskell? Okay, that's like half of the people that just raised their hands a second ago. There's 3 different kinds of exceptions in Haskell: imprecise, synchronous, and asynchronous. We're mostly going to focus on the last one. I'll just go over them really briefly. If you're new to Haskell, this is a little bit overwhelming. And I took 10 years before I took a look at asynchronous exceptions. But don't panic. We can classify them fairly easily by where they come from. Imprecise exceptions come from pure code. They bubble up to I/O, and then you can catch them there. We're not going to talk about imprecise exceptions for the rest of the talk. Synchronous exceptions come from I/O code and are caught in I/O code. And there's a trend. And asynchronous exceptions come from other threads and are caught in I/O. That's the trend. They're all caught in I/O. From the I/O perspective, they kind of all look the same. But they come from other threads. That's a bit different. They're originally introduced to deal with thread cancellation, meaning that they're a termination signal. When you get one of these asynchronous exceptions, you should crash, or you should regard yourself as about to crash. The conditions under which you might get them is you're running out of memory, you're running out of heap memory, which is a different limit, apparently, or you've been canceled by another thread, likely the main thread, whoever your parent is, or Control-C has been pressed. So let's go through a brief example. Synchronous exceptions, in this context, we want to know if you acquire a resource, use the resource, and release the resource, are you going to leak things? And so that's the question we want to know. Can we jump out of this code block in any way without releasing the resource? And of course, everybody here who raised their hand and understands exceptions can say confidently that, yes, if you get a disk on fire exception in the middle of using the resource, then you will jump out of this without ever executing release. And so this is no good for synchronous exceptions. And so we might add a bit more complexity here. And anybody who has looked at the source code of base, particularly the exception module, might recognize this as about like 90% of the bracket function, substituting some implementations in. But if we change the code to look like this, where did my pointer go? There it is. You might acquire the resource, go over and use the resource, and if you're lucky, get down and release it. And if you're unlucky, well, you catch and you release it. You rethrow the exception, and that prevents you from releasing it a second time. So this looks good. Can we leak the resource? And you're all probably saying, well, no. At this point, you've solved it. Now let's throw a wrench in the gears. We're only going to talk about asynchronous exceptions for the rest of the talk. Can this leak the resource? Can somebody tell me if this is going to leak the resource? Just shout it out. Yes. Where should I draw all the little bombs? Yeah, everywhere. It can leak the resource here, 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 and here. No, so in this case, before and after using are going to be under the catch And so those will not leak because they'll go in here. Oh, I see the projector is a little delayed. They'll go in here and they'll release. But the lines before applying the catch and after applying the catch, or the spaces between lines, could be places where the runtime would raise an exception and then you would not release the resource. And at this point, why don't we just give up? I mean, I understand mask exists, but this is a bit too much. I don't want to write code looking over my shoulder all the time. So now for a brief interlude into distributed systems and the actor model. So when we're talking about distributed systems, we often draw diagrams like this with a big arrow pointing down that indicates time. And we label processes. So this is process 1 running a long-running task. And sometimes you might want to not run the task yourself. Perhaps you have other work to do. And so you might send a message with the lateral arrow here to another process and have that process run the task for you. And then when that process finishes, it'll send the message back to you. And message passing is pretty important in distributed systems, also in actor systems. We can use these diagrams to also talk about actor systems. You just change the P for process to T for thread. And now instead of sending a message to an existing process, let's say we're forking, we do the long-running task, then we get a result back in the form of the other process quitting, which is like the other thread quitting, which is like a join. But let's say you care about whether or not the long-running process is taking too long. And so you have a timer. And at the end of the timer, you send a kill message over to the other, you send a kill to the other thread. You have this in Haskell in the control.exception or control.concurrent library called kill thread. And it's implemented with throw2, which throws the thread killed exception. But as we've shown above, you can catch exceptions. So what if you just didn't get killed when you were asked to be? What if you just didn't do what you were told? Well, yeah, you can catch exceptions. You can do what you're not told. And you can do it a lot. I mean, what if we had a whole bunch of threads and they were all just saying, well, I'm going to catch these exceptions. I'm not going to do what I'm told. This is starting to look a bit fishy. This doesn't even look like exceptions anymore to me. I mean, all right, so with that introduction, now we're going to implement the actor model very briefly. We're going to use the exceptions, and I want you to interrupt with questions, because the next couple of slides have a bit of code and are a bit confusing, or a couple slides onward. All right, so we need 4 primitives. These roughly correspond to the things that Hewitt once told us are an actor system. We need to make a new actor. We need to be able to kill a running actor. We need to be able to send and receive messages. And Hewitt also, I think, said that actors need to be able to change their behavior. So we've already seen 2 of these primitives. We're going to fork IO to make a new actor. We're going to kill thread to kill existing actors. So we need 2 more primitives. We need to be able to send messages and receive messages. You can probably guess what send will be. Receive is going to be like a main loop. So on your thread, you'll fork and you'll drop into a main loop. We call it run actor here. And that main loop, you'll give it a handler. And the handler is defining the behavior of your actor. The handler will take messages, do some stuff, and then quit. And the loop will run your handler again later. The stuff that you might do is sending messages. So we're going to give you send and run actor on the next couple of slides. And all of this is already in the GHC runtime system. We're using fork IO, kill thread, throw2, and catch. We're not introducing anything new. All right, so let's do it. The first thing you probably want in your actor system, or your actor program per se, would be to define a message type that corresponds to whatever your domain is. We're not defining that here. We're just saying that it's there. And then you say instance exception, and suddenly magically it's a message type that you can send from thread to thread, because the exception system is extensible, which is really cool. And then the send function is rather simple. Hold on, let me A to reduce that. There we go. Yeah, it's just throw2 in this talk. In the paper, it's a bit more. We do some interesting stuff with that, but here it's just throw2. We're not adding anything new. So let's look at the run actor main loop. The main loop is going to take a consume function. The consume function is your function. It defines how your actor is going to behave. It's the handler that receives a message and deals with a message, does something fun. The first thing the runActor function does is it masks asynchronous exceptions. That's the other part of bracket that I didn't mention earlier when I pointed out that that was 80% of bracket. After you mask, we're dropping into a loop with an empty inbox. That's what the little empty list is for. Here's our proto loop. Our proto loop takes an inbox, and then if it's empty, goes to sleep. If it's still empty after we wake up, then we're just going to continue our loop. If our inbox is not empty, we're going to pop off the first message in it. We'll consume the message and return the remainder of the inbox. Again, looping around. I haven't said anything about catching exceptions, but this more or less handles the simple stuff. Now let's think about catching exceptions. So I've just wrapped the cases that I showed you a second ago with a catch and added an exception handler. So now we kind of have three cases if you squint. We have the case that you sleep, the case that you process one message, and the case that you get a new message and append it to the end of the inbox. If in either of these first two cases we receive a message or an exception, sorry, I'm going to start conflating those, we will drop down into the handler and simply append it. And in any of the three cases, we return the next inbox and loop around and continue. Why does this work? It's not in the type of sleep. Sleep doesn't exist, sorry, thread delay. Thread delay is too wide. It's not in the type of thread delay, but thread delay is interruptible. And it's not in the type of the functions that you're probably calling inside of consume, such as print or send or other sorts of functions you might call that do I/O. But consume is potentially interruptible, and we don't know. And what this means is, if at any point during the running of sleep, or if at certain points during the running of consume, an asynchronous exception arrives at the current thread, we will bounce out of these red parentheses down to these red parentheses and add the new message to the inbox, loop back around. That's all fine for sleep. If we're sleeping, we didn't have any messages, we weren't doing anything. We were just waiting for a new message to come. But if we were in the middle of consuming a message, let's say in the process of consuming a message I needed to send to you and to you, maybe between the two sending, I bounce back out of the consume, I get a new message, I add it to the inbox, and I loop back around. If I've done that in between, that means this X here, this one I was in the midst of consuming, didn't actually get removed because I bounced down here and used the whole inbox. So this is a buggy framework. This is a framework where you might process a message twice. In addition to that, we support a few other features in the paper. We use a wrapper data type to distinguish real exceptions from messages. And we put inside of the wrapper data type a sum exception. And the sum exception gives us dynamically typed messages and makes actors extensible, meaning that you can have them receive new kinds of exceptions without actually changing their code. We also encode state transition into the framework so that you don't need IO refs or anything like that. How am I doing on time? Chair? Time? Good. Okay. 15 minutes is way slower than I'm normally talking, so I need to do this part fast. All right, so in distributed systems literature, there's an algorithm called ringleader election. You wouldn't necessarily do this with actors in practice. It's not very useful for actors, because on a single computer, you could just generate a random number. But in the ringleader election algorithm, our goal is to pick a leader. So if you have a bunch of nodes in a distributed system, those nodes with a ring topology in the network, each node knows its successor and has a unique identifier, but they do not know the number or the identities of anybody other than their successor. The ringleader election's goal is to find a leader, which is finding an extrema in this ring. So the way it starts is any node decides to start the election by nominating itself to its successor. It's the only thing it really can do. Its successor then evaluates whether or not that's a better leader than themselves and forwards a nomination or produces a new one. So here, 2 has nominated itself to 1, and then 1 has decided that 2 is a better leader than 1, and nominated its 2 to 4, and 4 has said, no, 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 I'm better. So these nominations go around the ring. When we get back up to 1, 1 decides, well, 5 is better than the leader that I previously concluded was good. And so 1 replaces their desired leader. 4 does the same, 5 is better. And so we get back to 5. So now something different happens. 5 is receiving a nomination for itself, which at this point we know that the nomination for 5 has gone all the way around the ring, and everybody's best nominee has been 5. And so the algorithm is complete. So now I can show you a quick demo of this algorithm implemented using our little actor framework. Now, as I said before, the paper includes a bit of additional complexity. That is, we support stateful actors. The algorithm that I just showed you mostly just passes around a nominate message. In order to set up the topology of the ring, we also have this uninitialized state and an init and a start message. And I'll just very briefly show you the pure function that represents, or sorry, it's not pure, the pure-ish function that represents the actor's behavior. The first 2 cases, if you're uninitialized and you receive initialization, then you become a member of the ring. The topology is being set up. The second one, if you're a member of the ring and you receive a start message, then you nominate yourself to start an election. And the third one is the one that we just talked about. The third one is, if you're a member of the ring, you receive a nominee message, and you are the nominee, then that means the nomination has gone all the way around the ring, and the algorithm is complete. If you're less than nominee, then you simply forward the message, because the nominee that you received is better option. Or if you are greater than the nominee, then you make a new message nominating yourself to your successor. And that's pretty much it. Cool. So we ran it with 5 nodes, and it generated a random order that's not very interesting. Let's do a different one. That's not interesting. That's still not interesting. There we go. OK. So the random order of the ring topology is 9, 10, 8, 12, 11. And thread 7 is going to set things up for us. So thread 7 tells everybody who their successor is, and then says start to thread 9. And the algorithm that I showed you on the slides are these. I'm not going to go through all of them. But so 9 says, I nominate myself to thread 10. That's my successor in the list at the top. And then 10 says, I nominate myself to 8, because I'm better than 9. And then 8 says, oh, sure, I nominate 10 to 12. It goes all the way around the ring. It's not that interesting to go through all of these, so I'll call that the end of the demo. How did we get here? Well, in 2001, we got asynchronous exceptions in Haskell, which gave us the ability to throw to an arbitrary thread to cancel the thread. And we could only throw built-in exceptions, which is the key detail. It also gave us the ability to catch, but not just catch to clean up the database connection and then terminate, but catch and recover, meaning we could catch the exception and continue running. And then in 2006, we got the ability to take any data type and turn it into an exception with that one-liner instance exception my data type name. And you put those 2 ingredients together, or 3, depending on which you're counting, and you get this framework. So just to wrap up, this is built into the runtime. The actor ID is the thread ID. There's no channels or locks to be spoken of, except for the fact that they exist. They're just in the runtime. And there's no real imports besides things that are in base. It's just control.concurrent and control.exception, and then some bookkeeping. And you can do this with any data. Some things that are maybe not so good about this is we've opened a magical trapdoor from the land of if it compiles, it works, to the fairyland of dynamically typed spooky action at a distance with an unintended communication mechanism, which I kind of love. Duplicate deliveries are possible, but we can actually fix that by forking the call to consume. And now duplicate deliveries aren't possible because you can't interrupt the other thread, unless the other thread, who's anonymous. Anyway, you can get around that. And the sender blocks until the recipient has enqueued. These are asynchronous exceptions, sender blocks. Anyway, that's fine. You can avoid that too by forking whenever you send. And it's slower than channels. Yeah. I'm putting that under the less good column, right? This isn't a good framework. It's slower than channels. What we expect, that the unintended communication mechanism is slower than the intended communication, holds true. Except not always. If you overload the RTS with way too many threads, apparently the exceptions are faster than channels. I don't know why. Sorry. Future work. Figure out why this is sometimes faster than Chan. I have my theories. I'm not going to propose them unless somebody asks. Compare the performance with T-channel, the SDM implementation. I have no idea what will happen then. I haven't done that yet. Our paper has lots of graphs on this. It's kind of fun. Now that we have, I think, a GHC 9.61, we have delimited continuations. So we could probably implement this with delimited continuations, and then we don't have the double send issue, which is kind of fun. Because basically, I think if we catch an exception, maybe there's a way of accessing the continuation from within the consume method. And if we store that along with the state and the inbox, go back around, we can just resume that rather than processing the next message. Yeah, and maybe some future work is to limit the power of asynchronous exceptions in GHC. I'm not really sure. It's up to y'all. Thank you.
Any questions for Patrick? Please walk to the microphone and remember to share your name and your affiliation for our online audience.
Right. Hi there. Simon Fowler, University of Glasgow. Really lovely talk. Quite funny. I was wondering, do you think, so in Erlang you can monitor or link to another process where you can detect whether that process has gone down or terminated? Is there any way that you think that you could abuse the GHC runtime system to do that?
You mean detect if another thread has crashed?
Yeah.
Yeah, so this is one of the primary things that Joe Armstrong says is necessary, is the ability to detect when another thread has, when an actor, I don't think he calls them actors, has terminated. And in our case, the way that you'd approach that is by using finally on the end of the actor. So I skipped over it, but up here where I actually run these things, I'm calling run actor. And that's just an IO action, and I'm passing it into this function that sets up the topology. And so I think what you do is you'd put a finally here, and that would notify somebody who bookkeeps who's alive and who's dead. I'm not sure what actually, I haven't tested what happens if I throw an exception to a thread that has died. But maybe that causes problems and would be detectable. I'm not sure.
Okay, brilliant. Thank you.
Stephen Dillon, Jane Street. Sure. Firstly, this is horrifying. So well done, nice work. Second, you mentioned that the mechanism is slightly unreliable because of the possibility that some of the exceptions get swallowed by consume, and you had a workaround for doing the consume in a fork IO so that happened off some other thread. Have you thought about how you might like to extend the asynchronous exceptions mechanism in GHC so that you could do these things reliably?
Thank you for the question. I think the question is, can we lean into this?
Yes, of course.
Well, okay. So for the first thing, so we're not actually swallowing. We're not losing an exception if consume is interrupted. What we're losing is the partially processed current message will become reprocessed. So we're losing the progress that happened. So I guess what you're saying is, can we fix that?
Yeah.
Yeah. Well, so I mean, you can fork, and that fixes it. I mean, that's literally in Simon Marlowe's paper. Is the two caveats that I gave here, credit where credit's due. Avoid by fork.io of consume and avoid by fork.io of send. These are basically written in the footnotes of these 2 papers. And they work, because fork.io is not interruptible. What's interruptible? I don't know. It's in the documentation. So like you can get around it. I'm not sure if you would need to extend the exception system to solve the problems, because like the tools are already there.
Okay, thanks.
Yeah.
All right, so we don't have any online questions. So let's thank Patrick once more.